All right, so today we are doing on Anova. So what do I do? Okay. So when do you use Anova? When do you use Anova? Anyone? When do you use Anova? Your one-way Anova? Answers? Compare means. So why isn't t-test also used to compare means? More than two populations. Yep. So Anova is generally for more than two population. Generally to compare means for more than two population or more than two samples. Okay. Now, is it actually possible to use Anova for just two samples? Is it possible? Yes, no? Yeah, actually you can. You can use Anova for two samples. Okay. So later I'll show you what is then the relation with Anova for two samples versus the t-test that you have gone through last week. Okay. But generally Anova is for more than two samples. Is there a limit to how many samples Anova can handle? No. Okay, so there is no limit to the number of samples. It doesn't matter whether it's two samples, 5 samples, 10 samples, and so on. Okay. And because of this, the null and alternate hypothesis of Anova is standard. Okay. The null hypothesis of Anova is that all the means are equal. Okay. The alternate hypothesis for Anova is also the same. At least one mean is not equal. Okay, we'll talk what? Huh? Which one? We're talking. Okay. So alternate hypothesis is at least one of the means is not equal. Assuming that you reject, let's say the conclusion is you reject the null hypothesis, you accept the alternate hypothesis. It doesn't tell you a lot of things. It just tells you that at least one mean is not equal. Okay. Two things it doesn't tell you. Number one is it does not tell you, number one is which mean is not equal. Okay. Let's say there are 5 samples, A, B, C, D, E. If you reject the null hypothesis and accept the alternate hypothesis, it just tells you that at least one mean is not equal. It doesn't tell you which one is not equal to the rest. Is it A not equal to B, C, D, and E, or so on? Okay. Second is, it does not even say, does not tell you whether there is one or more means are not equal. Okay. So for example, there's A, B, C, D, E, and you reject null hypothesis, accept alternate hypothesis. It doesn't tell you that only one mean is not equal to the other 4. It can be A and B not equal to C, D, E. It can be A and C not equal to B, D, E, or any other combinations. Okay, so it doesn't tell you a lot of things. And because of this, the null and alternate hypothesis is kind of just standardized for that. Okay, so that is the first context we want to do. Now, hopefully you have all done the lab number 7, your R already, because now from now on, you're almost maxing out the statistics capabilities of Excel. So today we are doing half on Excel, half on R. Regression also half on Excel, half on R. Then subsequently everything on R already. Okay, so let's go to your diabetes data set first. Okay, now what you have to do is you don't auto-save the file. Okay, later some of you are going to have problems importing the data set into R because you do not have the clean file anymore. So if you do not have, make sure you download a copy. Okay, or later you just make a copy. So what you do is, for example, I want to test a hypothesis. Okay, my research question here is, let's say, so my research question is whether the average, let's say, glycosylated hemoglobin, whether is the same for all body frames. So here I have small body frame, medium body frame, and large body frame. Okay, so that is my research question. So my null hypothesis is then saying that the means, okay, or rather the average glycosylated hemoglobin is the same for all body frames. The alternate hypothesis will be at least one of the means is different. At least one of the body frames has a different average glycosylated hemoglobin. Okay, so this is the kind of data that we are looking at. So in Excel, what do I have to do first? I have to make 3 columns: small body frame, medium body frame, and large body frame. Okay, and it should fill with data for my glycosylated hemoglobin. Same as what we do for t-test. And because this is the way Excel does it, it's actually a very poor way of doing things. Think about when you want to do another test, you got to reshuffle all the data again and again. Okay, so we will talk about that in your R. So let's do your glycosylated hemoglobin and body frame. Okay. So remember how to sort it out. Go to Data tab, do a sort, and you sort by frame. So by alphabetical order, the large will come out first on top. So you take all the large body frame. Make sure you copy only the large body frames. Okay. And then you go to large. Okay. Then you go to the medium body frame. Yep. And small. Okay. So you have a small, medium, and large body frames done. Okay, then you can throw away the 2 columns already. All right. So make sure you got all the data right. Small, medium, and large body frames. Doesn't matter. Just get the A to Z or Z to A doesn't matter. Just okay. So the small body frame, just to check, let's say you click on it, column A, it should be 106. So it's actually 105 data points. That's the label. Medium is 190. Large, the count is 105. So make sure you have the same number. So make sure that at least the large body frame is 105. How many data points are there? You highlight column C, you should be count is 105. Make sure that you right. Look at that first. Okay, so Excel, although Excel can do two-way ANOVA, but it's actually very difficult to use. So we only use up to one-way ANOVA by itself. Later I'll show you how do you do two-way ANOVA and so on. Okay, so once you are done, you go to your data analysis tab. Look for the first one called ANOVA single factor. That's your one-way ANOVA. Okay, and you'll show you a dialog box that is very similar to your t-test. Okay, remember your t-test, you have variable 1 range, variable 2 range. But ANOVA doesn't have, because ANOVA, there is no limit to the number of samples you can have. Okay. So what you do is, you highlight, in my case, column A, B, and C. Highlight column A, B, and C in my input range. And my data is actually grouped by columns. That means one column, one sample. I can do the reverse, one row, one sample as well. Okay. Because I group by columns, so I tick a columns. The first row has the labels, so I tick labels. So this should be quite standard for you already. After that, my output range. Okay, my output range, let's say I put in D5, for example. Okay, or maybe I'm put it away E5. So once you are confident enough, just click OK. Look at the results. So click OK. You should see your ANOVA table. Now, the very first thing to check whether it's your data you saw it correctly is to look at the summary. Do you expect 105 small, 189 medium, and 104 for large? Okay. So if that, then it's fine. The second portion is this ANOVA table. That is the ANOVA table that in your tutorial or in the test you have to fill out yourself. And what you need to fill up is essentially all the different items. You will fill up to this F statistic. All right. So based on this, you have two sorts of variation. One is between groups, one is within groups. Between groups is the degrees of freedom is the number of samples minus 1. So you have small, medium, large, 3 samples minus 1, you have 2. And it gives you the F statistic. ANOVA gives you as the F statistic is a P statistic. And from F statistic, you have the P value. So based on this p-value, do you accept or reject the null hypothesis? Reject, correct? You reject null hypothesis because it's less than 0.05. Okay. So here what you say is, since the p-value is less than 0.05 or the critical value, okay, you reject the null hypothesis. So you accept the alternate hypothesis. Which then what it means, you just repeat the statement for your alternate hypothesis. Therefore, at least one of the body frames has different average cholesterol to the rest. At least one of the body frame has different average cholesterol to the rest, but it doesn't tell you which one is different from the rest. If we look at the average cholesterol level between small, medium, and large body frame, they are almost equidistant to each other. Right? Small body frame, you have about 5 milligrams. Medium, you have about 5.66. Large, you have about 6.15. So it's about equidistant from each other. So how do you know which one is different from the rest? Or is 3 just different from each other totally? How do you know? What can you do? So now you see that at least one is different, right? You have to find out which one is different. Because that can be quite interesting. Is small different from medium? Is medium different from large? Is small different from large? The easiest way is to do t-test for each one. So you do t-test between small and medium, medium and large, small and large. 3 times up, correct? But this, it can be a bit messy. Let's say you have 5 samples. How many t-tests must you do? No? 5 samples. A to B, A to C, A to D, A to E. So you have 10 times. Okay? So it can be a bit messy. Okay? That's how you actually find out which one is different from the rest and so on. Okay? Any problem with it here? Do you know how to do your ANOVA and interpret the results? Okay, so in your lab assignment, task 2 asks you for the total cholesterol. Oops. Yeah, this is glycosylated hemoglobin. Okay, so I read wrongly. So this is the average glycosylated hemoglobin. This will be funny. So why not you repeat the same thing for the cholesterol? Okay, so you take the cholesterol and body frame, you separate into 3, and you repeat the same thing all over again. Yeah, it's messy. Correct. So no choice, that's how you have to do it that way. So we'll settle all the Excel part, then we go to the R part. Okay, so what you need for the next one is you look at cholesterol and body frame. Okay, so let's look at it first. Small, medium. Okay, so I will just do my Anova. So you do everything correctly, you will get this result. Okay. Any problem here? What should be got? No problem, right? You get your p-value to be correct. Okay, so now my next question is, based on the table alone, how many what's the minimum number of samples Anova can handle? Does it need to be 3 or can it be lesser than smaller than 3? What's the minimum then? Can it handle just one sample? Do you think it can handle just one sample? Cannot, right? Because why? If it's only one sample, then the degrees of freedom here will go to 0. So the minimum number of degrees of freedom is 1, which means how many samples it can handle? 2, right? So let's just try what happened, what is the relationship between your t-test and Anova itself? Because t-test, you also do 2 samples. Then what's the relationship between these two? Okay. So we just grab the small and medium, go to another worksheet, just the small and medium, and you do Anova based on this, just small and medium. So in this case, your null hypothesis is that the average cholesterol for small body frame equals to the average cholesterol for medium body frame. The alternate hypothesis is not equals to, right? So the alternate hypothesis is not equals to. So now the hypothesis looks like it is a two-tailed test or two-tailed t-test. Remember, Anova doesn't have one tail or two tail, it's always two tail. So let's do Anova here and see our results. Okay, so you do it, you get this result. Yep. Select from C and D, including C and D. All right. So all of you get this result already? Okay. when you do your t-test, what is the first thing you have to do before you get to a t-test? Huh? Your f-test. You check for equality of variance, right? Did we check for equality of variance for ANOVA? No. So do you think that ANOVA is considered using equal variance or unequal variance? Equal variance. ANOVA doesn't use unequal variance. Remember just now we have three, small, medium, large. Let's say you do your f-test, equality of variance. If small, the variance for small equals the variance for medium, but the variance for medium is not equal to the variance of large, then what do? So it just use your equal variance instead. So let's try just using equal variance, do your t-test for this, and see what happens. Okay. Just go directly and use equal variance. Okay, so you get this result. What do you realize about these two analyses? What is similar or what is identical? The mean obviously have to be identical. Any more? Look at the analysis results. What is identical? Okay, the first thing you realize is the mean sum of square, the within group mean sum of square or the error mean sum of square is the same as your pool variance. So that's one thing. These two numbers are identical. Okay. Actually, the calculation for pool variance is mean sum of square differences. Mean sum of square for error. Then you realize that the p-value for two-tail is also the same. So if the p-value for two-tail also the same, there must be one relationship that's missing here. What is the relationship between the F statistic and T statistic? These two green boxes. Anybody can see the difference or see a similarity? What is the relationship between these two? There must be a relationship between these two so that you get the same p-value. Essentially, if you've done your ANOVA tutorial, your p-value, the F statistic here is the mean sum of square between groups divided by within group to get here. Right? Your T statistic is somewhat dealing with the means divided by something with the pool variance. So there must be some relationship between these two numbers as well. The two green numbers. In order to get the p-value to be identical. What is the relationship? Just look at it. You can see it quite clearly already. Huh? Which one? Yeah, you're getting there. What? Which one? This. Yeah. So you square the T statistic is equal to the S statistic. You take this square, it will be equal to this. 7 times 7, where got 7 times 7? Equals this times this. This use this. Don't argue. Take a calculator and calculate first. Okay. All right. So that is the difference. Okay. So essentially, the F statistic here, it is the p-value is actually using the F statistic, degrees of freedom 1 for the numerator and degrees of freedom 292 for the denominator. When you go to your T statistic, the degrees of freedom for the numerator in F statistic is always equals to 1. Correct? These two is always equals to 1. And the degrees of freedom here is the same as the degrees of freedom for the denominator. That is why all these relationships are the same. So what it means is, if you do one-way ANOVA for 2 samples, okay, it is equivalent to 2 samples t-test, assuming covariance. Okay, so that is the relationship. So it's actually not wrong that after your F statistic, your F test for equality of variance, you say that it's equivariance, you can use ANOVA as well. It's not exactly wrong. Okay, because it's an equivalent test. Okay, so far any problem? All right. Now that's all for your Excel part with your analysis of variance. It's actually quite simple. There's only one test to do here. The next thing where we want to go is to use your R now. Okay, so go and open up your R Studio. Okay, go and open up your R Studio. Okay, so you have this. This is how your R Studio looks like. Supposed to override it. How to download R? How to download? Yeah, download R, then download R Studio. So yours is R, you haven't downloaded R Studio yet. Because it comes with 2 versions. Oh, the same thing. One is using your 64-bit, one is 32-bit. Yeah. No. This is R GUI, not R Studio. Can you see the difference? How? You download? You download R? Which part R and R Studio do not make the difference? This R already download. Then you go and search for R Studio. Yeah, so you have to go and get data and step. It's in files, option, and so on. So this is R, still R, right? R still okay. So that's so you put it inside your application before you open it. It's fine. Then you close it, put it inside application. Okay. Okay, so the next thing is you have to know exactly where you put your diabetes data set. Then I can't help you as well. It's your computer. Wow, this guy. Funny. You have to manage your computer properly. Okay, so let's say for my case, my data file is inside this folder. So you go and figure out what is this folder. The easiest way is you go here, right click, you copy the address as text, then use for example your notepad and figure out, paste the whole thing. That is the whole address. You have to know where you put your data files. Okay, so using this, you have to know that it's in the C drive, user folder, model, and so on. Where to actually find it? Because you have to get to the correct location inside R as well, using R. So here, okay, I'll show you how I do it. You go to R Studio, go to Sessions, go to Session. Are you in the right one? Okay, then go to Set Working Directory, and you choose Directory. Okay, so click on this Choose Directory, then you figure out where on earth are you. Cannot. You can, if you know how to do it. But at this moment, you can't. Yes. Because the file is actually not something that you can open directly in R. You have to import the data. Okay, so this is where you have to know exactly your location. Yes. Huh? All the way up. Hey, your screen is only one A4, you know. Okay, so once you get to a correct location, just click open, it will not show up anything there. Okay, once you click on open already, then the same folder information will be listed here. This is what you want, this is what you need.
Yeah, import, right?
Later, one step at a time. They get to here first.
Wait, what do you click on?
Okay. Go on. Okay. So once you are there already, this is the diabetes data set you want. But since I put it in as a CSV file, it makes your life a bit easier. So it depends on, is it a CSV file or is it an Excel file? If it's an Excel file, it's also okay. Make sure that it's the correct Excel file in the first place. All right. So if it's an Excel file, or if you don't have the Excel file, what you do is you go to your diabetes data set in Excel, copy the whole diabetes data set, copy it out, put it into a new workbook, and you save it. Okay, you save it as diabetes. Which means that in future, when you do any form of data analysis, the original data file, you do not change it. If you want to do any analysis, you copy out the data to another file and you work on that. The original file, don't touch it at all, just in case you mess it up.
What do you say? Click the data set, then new file.
New folder, new. No, you cannot do it here. You can do it in Excel. You're trying to save something in Excel. Okay. Yep.
I see you right now. I see you.
Huh? Later, once at a time. You get there, it's fine. Okay, so anyway, if you have the diabetes CSV file or the Excel file, you click on it, try to import the data set. Okay, import. Now, follow step by step. You click on import first, then download. No. This is all. Okay, so make sure that you get to this point first. It's all. Okay, that means you have actually saved the right file. Go to change your sheet. Change your sheet name. Okay. So anyway, you should get all this first. But what is important is you change the import option to just diabetes. Some of you have that underscore one, underscore something. Just remove those.
So I also.
Yes. Huh? Okay, don't bother with that. Yeah, that's fine. Yours? No idea. So you close and restart again. Okay, so once you have that, make sure that the name is diabetes only. Okay. Then what you do is you click on import. Yep. So once you have imported the global variable here, you have the diabetes data set. Tells you is 398 observations, that means rows. Each row has 19 columns, 19 variables. Okay. So here it will show up the diabetes data set for you. But you don't really need that. So you kind of reduce the space. Doesn't matter here. So I reduce it. Okay. Now R is a command line tool, which means you have to learn how to type commands. Okay, it's more stringent than Excel. I told you here you remove the underscore. Just pull the whole thing over. Okay, so now if you go to your hey, so let's refresh in Excel. You want to do Anova. What is always a problematic part? What is the easiest part you have to do all the time? You have to transfer data here and there, right? Okay. Let's say you do one for glucose, you do one for cholesterol and all this. You keep having to sort the data from one column into multiple columns. And that tends to be error prone. Okay. So in R, we don't have to do that. So for example, we want to do the same thing. We want to look for is the cholesterol level, is the average cholesterol level for the three body frame equal or not equal. Fundamentally, that's question one. Okay. So the function to do it is AOV, analysis of variance, and type exactly what I placed here, cholesterol. Cholesterol varies is this theta sign, not minus. Theta. Analysis of variance. Okay. By frame. Is theta not minus? Huh? Not grade P. Okay. So anyway, data equals to the data. Which data set you want? Is diabetes. And some of you have diabetes _1, then you have typed the whole thing in. Not yet, not yet, not yet. You can enter later. Okay. So this analysis of variance is actually a model. So you have to put it into a variable. So let's call the variable as model equals to this. It's just a variable. You can call it anything, it doesn't matter. Yep, after that you enter. It comes out nothing. That's fine. So make sure you have all this. What do you mean no backspace? Then is your computer have problem? Huh? Then you close bracket now lah. Close bracket and press enter. If you never close a bracket, here instead of this cursor, it will give you a plus sign. That means you have not completed the function yet. Then redo the whole thing lah. Yeah, type below. Yeah, close the bracket. Okay. All right. So basically, Anova is a statistical model. What we want is the Anova table. To print out the table, we use this function called summary. And the parameter is this model. Just enter. That is your Anova table. Okay. Yep. Yeah, that's Anova table. So let's say we want to repeat just now what we do for glycosylated hemoglobin. We don't have to resort the data again. We just change cholesterol varies with glycosylated hemoglobin varies with frame. You can do that. Okay. So now what happens if you want to check is the average cholesterol between locations equal or not equal? Huh? So which one do you want to do? Now instead of vary by frame, you want to vary by location. So two locations, Buckingham and Louisa. Right? So all you need to do is you change the model itself. Instead of by frame, you change to location. And how come you will recognize location? Because in your data table, the header is called location. The field name is called location.
Then enter, right?
Yes.
Then equals to summary.
Let's do a summary of the model that gives you or location. Okay. So that is one way Anova in Excel, in R. Now, what happens if you want to test this thing called two-way Anova, which is actually covered in a lecture, just that in the tutorial you never cover. So two-way Anova simply means that is it, let's say, vary by body frame and vary by location. You can actually do that. You just keep adding this part. So let's say I want to check my body frame and location. So location, I add frame onto it. So that gives me a two-way Anova. Vary by body frame and by location. So then you will generate one list of location, one list for body frame. So in this case, frame is still significant.
Actually, if you change the name to like one letter, it's very still big. Yes.
Yeah, but that's provided you can remember.
Wow. Now I say the word frame is more.
Yes, so it tells you that in this model, the location where the person comes from is not significant, but the body frame is more significant.
Is it judged by
The p-value. The p-value. So what happens? Remember, you have 2 locations, 3 body frame each. So by right, you can actually do a one-way ANOVA for body frame times location. So you can see whether it's a average cholesterol level for small body frame in Buckingham equals to medium body frame in Buckingham equals to large body frame in Buckingham, and so on. 6 of them. Also, right? Because it's 3 by 3, 3 by 2. Each location there are 3 body frame. So 2 locations there are 6 combinations. Okay. So how do you do that? In Excel, you have to sort by 2 columns, and then you keep pulling up. Here, it makes your life easier. All you need to do is you take the location, multiply by the body frame. Go up. Press up lah. No, not press the star. You times is actually this colon. Because times have a different use here. Times is combination. Okay. So, and so now your frame and location have actually 6 samples. Because 3 samples for Buckingham, 3 samples for Louisa. And it's still statistically significant. Yeah. So you can keep dividing. Okay. Why you cannot use times? For example, if I use times in this case, let's say body frame, and location. I can do frame, location, and gender, right? Because gender is also categorical. So let's see what happens if you just multiply. So here, gender. So this itself becomes a 3-way ANOVA. ANOVA can go multiple. There's no limits as well. So later we'll see what happens when you times it. ANOVA. If you do the regular times, that means you change here to multiply, frame. What do you think will happen? Everything combined. No, it's worse than everything combined. No, because remember, if you want to multiply, it's actually using colon, right? But if you use the actual multiplication, the asterisk, which is instead of multiply, it does all the combinations for you. So it does location, frame, gender. Then after that, it takes location times frame, location times gender, frame times gender, and the 3 times together. So that's 7 combinations. So this is what happens. 7 combinations now.
So the difference between the colon and the
Colon is you take the 2, match together, combine together. Yeah. So we have 3 columns. So now remember gender and location and frame. So you have 2 location, 3 frame, 3 body frame each. That's why you have 6 samples, right? If you multiply by gender, how many will you get? Because each one doubles. That's right. Yeah, exactly. So if you do that, then each one double sum. Your degrees of freedom becomes 11. It's actually 12. But we will not bother with all this so far. Just telling you that it's actually quite convenient to use it.
This is string. Like this.
Technically, yes, true and no. Because not technically, this thing can afford interactions. So all interactions are actually recasted into one way or another.
When would you want to use? When would you want to use component?
So it depends on your experimental design. For example, you can look at cell growth rate by what? You can look at cell growth rate by, let's say, you have three glucose, four, let's say 5 glucose concentration. Cell growth rate at 5 glucose concentration, right? That's already 5 samples. Within each of the glucose concentration, you can play around with temperature differences. So that's another one. Within temperature differences, you can have all the micronutrient differences. Yes. Why not?
Just use this.
Excel cannot do this. Excel will die on this already. Okay. All right. Okay. So the next thing is, there's actually some tests that you can try out. For example, in Excel, there's no such thing as normality test. You cannot check if the data set is normally distributed or not. Yeah. Here you can, in R, there's a lot of things you can do. For example, I can check whether is the cholesterol normally distributed or not. So based on your notes, I'm using this thing called Shapiro-Wilkes test. Shapiro test. But Shapiro test only takes one variable, so I use diabetes. So basically, I'm asking R to take the cholesterol column in diabetes data set.
What's the dollar sign?
In. So cholesterol in the diabetes table.
Sorry, you cannot find.
Okay. Yep. So basically, the Shapiro-Wilkes normality test tells you that it's actually not normally distributed. Because the p-value is lower than 0.05. It's not normally distributed. P-value is lower than 0.05. Okay. So that is one way of doing it. Then in R, we seldom use your F test for equality of variance. We use other tests. Okay? Because remember, F test is taught simply because it's the easiest test. Just one divided by another. The one that we generally use is this thing called Bartlett test. Bartlett test. So I want to test the cholesterol, whether it's the cholesterol of, let's say, male equals to female, the variances, the variance of average cholesterol, no, the variance of cholesterol in males equals to the variance of cholesterol in females. So cholesterol varies with gender. And then my data is my diabetes. Okay. So that tells me that the variance can be assumed to be equal. Yeah. So I'm testing whether it's the variance of the cholesterol in males equals the variance of cholesterol in females. Yeah. Because the value is more than 0.05. I cannot reject my null hypothesis. But varies with. Varies with. It's not variance. It's cholesterol varies with gender. Yeah, this Butler's test is actually to test whether is the variance equal or not. Okay. All right. Now, remember your F test for equality of variance, you actually cannot test for more than 2 samples, right? It's one over the other. But Butler test, you can test for more than 2 samples. I've just done it with 3 samples. So I'm checking is the variance of cholesterol for small body frame equals to a variance of cholesterol in medium body frame equals to a variance of cholesterol in large body frame. It's still, if you assume to be equal.
But it's less
Less than 0.05.
no, less than
Okay?
even
So it's equal.
Yeah, it's equal. The 3 variances can be assumed to be equal for
More than 0.05.
what?
More than 0.05.
Yes.
That's right.
Okay, so essentially that's all for today with R and Excel. Next week is your next week again.
Okay.
Yes, again.
Not enough, bro.
Then when we come back, we'll talk about regression. So regression, Thursday we'll cover the tutorial for Anova. Yeah, Thursday. Okay. Then regression is a very important topic as well. Okay. Actually, Anova is regression. Huh? Explain why? Okay, see because if you actually do, for example, is cholesterol proportional with glycosylated hemoglobin? Okay, you can actually do that. Okay. And if you do your regression, let's say your data, go to your regression. So this will cover. Anyway, we talk about regression. So Y range, can we actually predict the cholesterol level using the glycosylated hemoglobin level? Okay. Okay. So Y is the Y-axis is cholesterol level, the X-axis is glycosylated hemoglobin level. Okay, and we have labels. So upper range, I put in D1, and I just click OK. Okay, so it will give me an error because I need to highlight the exact columns. So it's a bit troublesome. Okay. So it doesn't allow me to highlight columns for whatever reason. Huh? What do you mean why? What do I do? I highlight the data rows. That means I cannot highlight the whole column. Regression doesn't allow me to do that for whatever reason. Just highlight lah. What do you mean how? First, you have here, right? Take this, highlight the whole column for only the data points. That's why it's from A1 to A399. Okay. Then you actually end up with a Anova table here. We'll talk about this when we come to regression. Okay. Yes. Actually, Anova is regression. Anova is regression. It's the same thing. Regression is not Anova. Anova is regression. Yep. How come it's so confusing?
Wait for it to come.
No, it's not confusing, I'm just stupid.
No, it's not stupid.
Let's wait for the casket.
Teacher can close the R already.
Yes, yes, yes. Why? It's so beautiful.
Need to save or not?
No need, don't save, don't save.
Why your arm got like 3D?
Because all we
What
done-
3D? I thought you
I see your icon is like 3D one, but our icon is 2D one.
don't know.
You want to upgrade it, sell my-
Okay.
What funny face, yeah. Eh, try to save or not?
No need, no need, don't save. Okay. So don't save. Yeah, don't save. You want to save also can up to you. You're never going to use it again. Okay. All right. So that's all for today. Okay. Then the rest. Okay. Bye bye.